Starting now. So hi everyone, welcome to week 8 of Techquitable. Today we have lecturers who are Hannah, Mark, and Marcus joining us to lead the lesson on trees and graphs. Just a little bit of background of these lecturers. So Hannah is a software engineer at Block, which is also formerly known as Square. They also have Cash App, which you may have used. Mark Kenji works at Trial Spark, which I believe is a medical clinical trial software company.
Yep, health tech.
Yep.
Generally, yep.
And then lastly, we have Marcus joining us. He's been with us ever since we started Techquitable 4 cohorts ago, but he is a technical lead manager at an ad tech company called Edo. But yeah, feel free to kind of introduce more of your background, because I'm sure you guys have more interesting stories to tell about yourself. So.
Cool. Thanks, OneTap, for kicking us off. Why can I not go? So welcome to today's talk on trees, binary trees, and graphs. Marcus, do you want to take this, or should I?
Sure, I'll start here, but if you could keep presenting.
Cool.
So as we're talking about, today's topic is graphs and trees. And I think it would be good to have a high-level definition of graphs. You've probably come across them at some point in your journey through CS, but I think it's good to have a definition that we're working off of. So at a high level, a graph is a collection of nodes connected by edges. Nodes contain values and can really represent anything, and edges represent some property or connection between a pair of them. So we have a quick visualization of a graph down here. I think it's worth thinking about what sort of things might we model as a graph. So one pretty common example is the Facebook friend graph. So if you imagine every person on Facebook is a node, and they'll be connected by an edge if they're connected as friends. And as you can see, this will kind of create the same relationship we have here. We could see like there are people here, person 1 and person 2 are friends, person 2 and person 3 are friends, 1 and 3 are not friends because there's no edge between them. But one's friend would be 3 going through 2. Similarly, the web is often represented as a graph where websites are nodes and they're connected by an edge if one has a link to another. That often would be a directed graph, and we'll talk about that in a little bit, but edges could have directions. So 1 could point to 2, but 2 might not point back to 1. And the algorithm that Google uses actually for like PageRank, for prioritizing search results, depends heavily on treating the web as a graph. And another quick example is flights. An example, cities are nodes connected by an edge if there are flights between them. And we'll actually work through a problem later today that works off of a graph like this.
So let's start with, or I guess, we can talk about how you might see graphs and trees come up in interviews. I think a good thing to look out for, kind of an indication that a problem might be a graph or tree problem, is like, do you have kind of information that is connected to other information? I think like once you see a few of those, it becomes pretty apparent like when a graph or tree might be useful. So often things to think about are like, how do I structure this as a tree or a graph? We'll kind of get to what trees and graphs look like in a sec. And then of course, once you have it structured in a graph, like how do you actually operate on that tree or graph? Like trees and graphs can be a little tough to work with in interviews. Like hopefully the operations that you'll be asked to do are not that complicated, just because it does generally take some time to implement these things, and interviews are not that long overall generally. But I think a little while later we'll talk about some kind of good things to practice on these data structures. One other thing to note is that unfortunately, this is one of those things that comes up in interviews much more often than it comes up in actual work. I personally get very excited when I get to use a little bit of trees or graph theory or something, but in like my 4 or 5 years in the industry, that has been only a handful of times. So but good to know. And yeah, let's start with trees. So trees are a special type of graph. They're kind of like a restricted type of graph that can be represented in a little more structured way because of those restrictions. Excuse me. And they're often used to represent things hierarchically. I think that's a word. So some things that are trees are like web documents, HTML. You have your base HTML element, then under that you have other elements like the head and the body. In the body you have like paragraphs and lists have elements, and elements have the bodies in those elements. Reddit or forums are often graph or tree-like. You'll have a kind of root comment, and then people can reply to that, and people can reply to replies, and all the replies can have like multiple replies under them. So yeah, a lot of information is kind of hierarchical just naturally. When it comes to trees, or graphs in general have nodes. In a tree, we have what's called the root node, which is kind of the start of the tree. And the root node has no parents. So here, A is the parent of B and C, B is the parent of D. So A is our root node, it has no parents, and C and D are leaf nodes, they have no children. Anything else here? The other thing to note here is that I think Marcus alluded to directed and undirected graphs before. So trees are directed. You can see that there's A points to B, B is the child of A, but it's not like a bidirectional relationship. You can't say A is the child of B. Yeah, let's see. Other terms, depth. Depth specifically applies to trees, not necessarily graphs. And depth is just the distance, the shortest distance to the root node. So the root node has the root node has a depth of 0, and then its children have a depth of 1, their children have a depth of 2, and so on. The height of a tree is just the maximum depth of any node in that tree. So here, the maximum depth is 3, so our height is 3. And then we might also talk about the different levels of a tree. So at the very top, the root node is the first level, or the 0th level if you want to index like a computer scientist. The next level is all of the root node's children. The next level is their children. Yeah. And just the kind of final thing before we get into some specifics about how to use trees are how we might represent them in code. So it's generally pretty easy. A tree a node just has a value or some data and a list of children. So I think that hopefully you are at least vaguely familiar with Python. So to create a node, we just pass it in some data, that's its value. And then we have this add child method that creates a parent-child relationship. So if we have these 4 nodes here, A, B, C, and D, we can make add B as a child of A, add C as a child of A, and add D as a child of B to kind of get what we have represented over here. And yeah, so node A is our root node here. That's generally the only one that we're going to like kind of keep a reference to, because once you have that root node, you can traverse the tree to get to all of your other nodes. So that's what we're doing here. We look at node A's data, and that's just A. Then we look at the first child of A, and we look at its data, that's B. Look at the second child of A, its data is C, because that's C node. And then we look at the first child of node A, which is D. That's all I had. Any questions on kind of trees in general or any of the terminology? Oh, wait, let's look at the chat. Oh, thank you, Lewis. All right, well, in that case, I think I'm gonna hand it off to Hannah.
Wow. Oh, I see things happening in the chat, but I'm assuming, oh, okay.
Just congratulating me.
Give
It's
it an all
okay.
clear. Okay, great. Cool. So I'm Hannah, and I'm going to go over binary trees. So binary trees are actually one of the more common implementations of a tree that you might see. So they are similar to a tree in that we have our parent node or our root node with children. As you can see with the general tree, we have a root and it can have multiple children, and its children can have multiple children as well. But a binary tree is different in that it can have at most 2 children. So it can have 0 children, 1 or 2, but no more than 2. So how this looks different in actual implementation is with the generic tree, we'll have our root node and our children stored in like an array. But with a binary tree, what you typically see is that self.left and self.right, just referring to the left child and the right child. So there will only be at most 2. So with the usage down there below the binary tree interface, you'll see that we are initializing the root with a value of 1. We're initializing a node left with a value of 2 and right with a value of 3. And then we are assigning the left and right child to our root. So can anyone tell me what this tree here would look like?
Okay, so it look like, so 1 at the root, then 2 as the left child, and 3 as the right child.
Yeah, so I don't know if I'm mirrored or what in the camera, but we would have the 1 at the root, and then to the left would be the 2, and then the right would be the 3. So yeah. So when and how do we use trees? There are specific types of binary trees. There's a binary search tree, which I believe the next couple of slides will go over that more specifically. But these are really good for searching. And that's because it's easy to tell where a specific value should be based on how you traverse the tree. It's also efficient in search and collision handling for hash maps and sets because, like I said, it's easy to tell where values are and if we already have that value in the tree. Another type of binary tree can be a heap or a priority queue. Heaps, if some languages automatically implement heaps, like Java, I think has one built in, but it's good for easily finding the maximum value in a tree or the minimum value in the tree, depending on the implementation. So it's an easy way to keep track of the top end of something because that will be your root value. Another type is a syntax tree. So this is good for like a calculator implementation. You can kind of represent arithmetic expressions where every operation is an actual node in the tree and kind of implement it that way. And then lastly, there's a Huffman tree, which is good for data compression. Yeah, I think Huffman trees can be, they're a little over my head personally, but yeah.
You should not run into one of those in an interview. That would be a bad interview.
Yeah, I've honestly never heard of a Huffman tree until this, so I actually had to look it up and see what it is, but yeah. Okay, so subtree, often when we talk about binary search trees or binary trees, we also talk about subtrees. Typically, anytime you have a definition or some sort of defining factor of a binary tree, it tends to also mention the subtree as well, kind of fulfilling those requirements. So a subtree is a tree within a tree. With this example on the right, we have 1 as our root node, but then also we can have the subtree where 2 is the root node, and so on and so forth. Any node in a tree can be represented as a subtree. Yes, and often with binary search trees, we can think of them recursively, which just kind of goes back to how each definition of a full tree versus the subtree is recursive and kind of fulfills one another. And then our base case would be the leaf nodes, because they're at the very bottom and they don't have any children. So that's how we know we're at the end of the tree. Okay, so balanced tree. This is an example of like a definition, like I said, that has also the left subtree and right subtree mentioned and how it's also fulfilling that definition. So the official definition of a balanced tree is the left and right subtrees heights differ by at most 1, same for the left and the right. And I like to typically say that if you can see a balanced tree, you can usually kind of tell when it's balanced. You kind of know when you see it. So the one on the left, if we go down to that first leaf of value 4, you can tell that that is at a depth, or it has a height, the whole tree has a height of 0, 1, 2 for the left subtree. And then for the right subtree, that has a height of 0, 1. So the difference there is only 1. So that means the tree is balanced. Notice that it doesn't mean that it's symmetrical. It really matters about the height. And then if we look on the right, this is an unbalanced tree because our left subtree has a height of 0, 1, 2, 3. And the right subtree only has a height of 0, 1. So that difference is greater than 1. So it is unbalanced. Okay, so specifically binary search trees. And if anyone ever has any questions, feel free to stop me whenever. So binary search trees, I think even more so, are more common, are the most common type of binary tree. So for every node, the values in the left subtree are less than the value at that node. And then the values in the right subtree are greater than. So we can see on that left example, we have 8 on our root, and all values in the left subtree are less than 8, and all values in the right subtree are greater than 8. And if we move down to the value, the node that has a value of 3 is also the same there. So the left subtree of 3 is less than 3, and the right subtree is greater than 3. Now, this is the reason why the example on the right does not fulfill this definition, because if we move to the value of 3, the left subtree is less than, which is great, but then the right subtree, we do have that value of 2, which is not greater than 3. So that is why that is not a binary search tree. Yep, so left and right subtree, each must also be a binary search tree. That's why the one on the right does not work. And so for time complexity, so the time complexity for binary search trees actually O of log n, and each step down the tree halves the number of elements in our search. So that kind of explains why it's log n. Does that make sense to everyone? Essentially, if you're looking for a specific value, every time you make a move, either right or left, you're cutting your potential nodes that you need to visit in half. So because that's continuously halving the number of nodes you need to visit, it is log n. So that is a good thing to like have in your brain for interviews, because oftentimes if you don't need to implement a binary search tree, just mentioning that, you know, maybe this implementation would be better if it was a binary search tree because it's O log of n. It's a good like buzzword, so to speak, but it does make sense and it is true. So, okay, so we have a couple different types of traversal methods for trees. Now, traversal just means that you're visiting each node exactly once. There is breadth first search and there is depth first search. So these are the two main ones. The depth, of course, having those subtypes of traversals. But just to give a brief overview, breadth first search, just think of searching wide before you search deep. So we're searching level by level, which is what we mean by level ordered traversal. We're just going one at a time. Whereas depth first search, we are searching down the leaves and kind of snaking our way through that way. Each one kind of has its own benefits, and depending on your problem, you may lean towards one versus the other for efficiency's sake. But oftentimes with tree problems, you can implement both types. It's just a matter of, when and why you choose one versus the other. Okay, so these next couple examples just kind of go through what a traversal looks like for these types. So for breadth first search, as I said, we're kind of just going level by level. So if you click through, it kind of highlights the nodes that we visit. So yeah, for breadth first, we start at the root and then we go through each level from left to right. So we go from 1, 2, 3, 4, 5, 6, 7, basically in counting order. Yeah, so that one's pretty simple and the same every time. The next couple ones, yeah, that's what it looks like. Oh yeah, so this is actually good to know. So breadth first search traversal, it makes sense when we look at it and how to do it just based off of a picture, but it is a little more complex programmatically to do that. So each node only knows about its own child nodes. So for example, node 2 knows about 4, 5, and eventually 8. And node 3 knows about 6, 7, so on. But node 3 does not know where node 4 is or how to get there. So can anyone tell me how we would be able to implement a breadth first search? What a good way would be to do it? It's a little tricky. Yes, so Saley, I hope I said your name right, said queue, a queue data structure, and that is exactly correct. So yes, our code is here, and the way this would work is we would set up our queue, we would add our root, so that was a value of 1 to the queue, and then we would start to actually go through the tree. So while our queue has a length, we would pop off top value. So in this case, it would be a 1. And we would check if that 1 has any children. So in this case, we had that 2 and that 3, and we would push those onto the queue to look at later. So at this point, we're doing whatever we want to do with 1. And that's what those two if statements are doing, is checking if it has a left child and a right child and putting it onto the queue. So then we would continue through that while loop and pop off the next value, which would be 2. And once again, we would check for the children and put it onto our queue. So the 2 had, I don't remember, it had a 4 and a 5. Excellent. So the 2 out of 4 and 5. So we push that onto our queue. So at this point, our queue looks like 3, 4, 5. So we've stored the 4 and the 5 so that we can get to them later, so on and so forth. And we continue to go through that queue until we don't have any more values. Does that kind of make sense a little bit? I think sometimes when I think about it in code, it doesn't make sense to me, but when I kind of see the picture and talk through that tends to help me, and draw pictures and stuff. Okay, if there are no questions. If that's looking good, we can continue to depth first search. So 3 different types of traversal. The first one we're going to do is in order traversals. So the things in those parentheses are really important. We're going to check the left subtree first, then go up to the root, and then go to the right subtree. So for this one specifically, we're going to start at 1, and we're going to do the left subtree first. So we're going to keep going left, 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 left until we hit the 8, and that gets highlighted. Great. Yeah, and then 8 is bottom, so then we go to the root. We check if 4 has a right subtree. It does not, so then we continue to do the same recursive search. So we go to the root of 2, check the right subtree of 2, which is 5, and then up to the root of 1, and we're done with the left subtree, so we go down to the right subtree, but doing the same thing. So we move right and then move all the way down to the left for 9, and then root 6, 10, and then 3, 7. So that outputs that order, kind of like that. So the next method is a pre-order traversal. Does anyone want to give this one a try, or maybe give a couple of numbers or something? So for this one, we start at the root first, and then we check the left subtree and then the right subtree. I can start us off if we need to. Go ahead.
Okay, so I think it would be 1, then 2, 4, 8, 5, 3, 6, 9, 10, and then 7.
Excellent. You did amazing. That was perfect. But yeah, just remembering that I think this one's a little tricky in that like my brain wants to not start with 1 since it's depth first search, but since it's pre-order, the roots first, you start with the 1. So yes, good job on that. And the last way is post-order traversal. So this is the last combination I think that we have. You check the left subtree and then the right subtree, and then you go to the root. So we can go through this one quickly, I think. So we do left of 8, and then since that 4 didn't have a right node, we go up to 4, and then do the right, and then the root of 2. And then we do the same thing on the right subtree, so 9, then 10 and 6, and then 7, 3, 1. Yes, I definitely needed a cheat sheet because sometimes I get these mixed up. So that is our output.
If it helps, if you don't mind me jumping in here,
Go
like
ahead.
this is also very confusing for me. So like when I try to think about the differences, it's like as I'm traversing this tree recursively, when do I kind of evaluate like any given node? So for if I go for here, go back a whole bunch. So if I go for pre-order traversal, right, I print out the value of my node before going into kind of its children. So right, I start with 1, and then I start with 2, or sorry, I start with 1, and then I go into its child of 2, and then I'm on the 2 node, and then I print out 2, then I go into its children, and then print out 4, 8, and then there's nothing else kind of in that subtree of 2, so I go back to 2, and then over to 5, and back up and back down.
Mhm.
But
Yeah, that
definitely
makes sense.
a little bit confusing to try to keep those
Yeah.
separated.
Yeah, and when you actually implement a binary search tree, I know recursively, I'm pretty sure iteratively as well, it looks similar. There's like 3 lines that you have. It's like outputting your value and then checking your children. And the difference between these 3 traversal methods is like putting these lines in different orders, essentially, which is kind of what you said.
Yeah, exactly.
But if you want to think about that in programming, that's how similar they are, but that's like how important it is when you output versus check your children. So. Okay, I think that's it for, oh yeah, okay, yeah. So for our traversal methods, the time complexity is O of n, because worst case, we visit each node once, and then our space complexity is also O of n, because that's determined by the tree's height. So for instance, if it was a binary search tree and we had like 1 at the root, and then we just went 1, 2, 3, 4, 5, 6, 7, 8, 9, and kept getting bigger, it would just be like a straight line. So that's why the space is O of n and the time. Okay, yeah, I was like, I thought there was one more. Yeah, so good things to practice with trees. Again, focus on the fundamentals and don't worry too much about the specific types of trees. Like we said, I've never encountered trees in my professional work. I've seen them maybe once or twice in various interviews, stuff like that. So they're definitely good to know. And when I was doing interview prep, it was just a good way to work my brain and to kind of get more familiar with the language and kind of better at doing problems, thinking about problems and doing them efficiently. So really practicing traversing a tree, whether that be iteratively or recursively, if you want some practice with recursion, or both, if you want extra practice. Finding the height of a tree is good to know. Getting all nodes at the same depth, determining if a tree's balanced, or binary search tree. So these are just all good things to practice. Again, not super common to see, but I think just good to practice and get better at interviewing and programming in general. So, and with that, I think we leave with a couple of links, and that's it. Yeah, check those out.
Great. Any questions about trees before we move on to the more general case of graphs? Yeah, trees are cool.
They're cool.
I fully agree. Cool. So yeah, we'll go on to talk about graphs. I think one thing I'd say is as thinking about this, I agree that, okay, none, it was clear. Awesome. Yeah, I think one thing I'd say about trees is, although you won't that often see like directly a tree structure where you have nodes and you have, you know, left child and right child and things like that, it is actually fairly common that the sorts of traversal algorithms, BFS, DFS, recursion, iterating through it, does parallel some things that I think you would occasionally have to do as a normal software engineer. So I think it is true that the exact tree structure doesn't come up all that often, but it is really good to practice, because you will probably at some point start doing a traversal and do something recursively and think, wow, this is actually sort of similar to some of the tree or graph algorithms. So with that, we come to graphs. Do you want me to take over sharing?
Oh, sure. Yeah, that's probably easier, isn't it? Let me stop sharing.
Great. I think we can do this. Great. Can people see the screen?
Yes, I can see it.
Awesome. Cool. So graphs. So we've already seen a case of graphs, and so trees is just a type of graph. And as we mentioned earlier, graphs are intended to represent any sort of data or collection or something where we can define connections between them. So some of the examples of common questions that you might have is there a path between two nodes? Or find a node matching certain criteria? Or what is the shortest path between two nodes? Maybe how many connected nodes are there? You know, starting from one node, how many nodes can we get to that are connected by the edges? So terminology, and we've been using these terms already pretty interchangeably, but I think it's good to make sure we're on the same page. So nodes are the points. Sometimes you'll see them referred to as a vertex, same terminology, exact same meaning. And then edges are the lines that we draw between nodes. So in terms of types of graphs, the kind of basic type is undirected. So this would mean any edge connecting two nodes is symmetric. So if A is connected to B, then B is connected to A in the exact same way. You can also have directed graphs. So that would mean every edge has a direction. So A pointing to B does not necessarily mean B pointing to A. So an example of something there that you might want to represent as directed graph would be a city with a lot of one-way streets. So, if you have a street corner and you have another street corner and you have a road going from street corner A to street corner B, that is one way, you wouldn't necessarily be able to reverse your path. You'd have to go around. And so a directed graph would be a better way to model that. Also unweighted, I think all of the graphs you've been looking at so far have been unweighted. Every edge is just an edge representing a connection, but you can also have weighted graphs. And that means that every edge will have some sort of weight. So very frequently this comes up in maps. So a weight could be a distance. So in this case, this could say the top node is a distance of 2 from the left node and a distance of 8 from the right node. Or it might be a cost of transferring data, or it might be the max bandwidth that it can support, or just the general idea is that you can store some value on the edge. Some of the ones in the bottom right are a little bit less important, sparse and dense. Sparse just generally means there are not that many edges in the graph. Dense means there's a lot of edges in the graph. Those are a little bit subjective depending on the graph you're working with. And the ones in the top right, I think, are an interesting property of graphs we can get, which is that once you start working with directed edges, you can start to get cycles. So you can see here in that, in the one that's labeled cyclic, if you start at that top node, you can go in a triangle and start spinning around forever. And that has great relevance when you're working with things like a depth first search. If you're not careful when you're doing your traversal, you'll get into an infinite loop, because you'll go from the top node to the left node, from the left node to the right node, from the right node to the top node, and around a whole bunch. Cool. So just for fun, can people start giving examples of graphs? And then maybe for each example, and you can do this in the chat, say whether you think it would make sense to represent it as a weighted graph or unweighted, directed, undirected, just anything that you think of in your everyday life or in CS, or anything that you think it might make sense to represent as a graph. You can feel free to reuse examples that I said earlier. Yeah, airports, flights, and cities. Yeah, so do you think it would make sense to represent that as undirected graph or directed graph? Directed, yeah, definitely directed, because a flight, just because you have a flight that might go from San Francisco to New York doesn't definitely mean that there's a flight from New York to San Francisco. You'd want to have a separate edge representing that. Roads between two cities, totally, and weighted graph that represents traffic congestion. Yeah, I think there's certain models. We're not going to go into this, but I think flood flow, maximum flow, that is used quite a bit on a weighted graph like that to represent traffic and actually model traffic conditions in like real time. Grocery shopping for multiple stores. Yeah, if you want to, there's all sorts of interview problems about, you want to pick, a store has a bunch of things you're selling, but no store has everything. So you're going to need to go from store to store. How do you optimize your shopping trip? That would definitely make sense. Roommate matching system, weighted graph. What might be the weights in a roommate matching system? Proximity. Yep, that would definitely make sense. Yeah, and there'd be a really interesting problem on, you have a graph of people where every edge represents how compatible they are as roommates. And then your task is to pick what roommate selection would be best to optimize the global compatibility scores.
I think
Cool.
also a really interesting one is like I don't know if you've heard of Snack Pass where like they actually bring like takeout to college students. So there the optimization like depends on so many different factors that can be like pulled together to form a weight, and then you can go through that.
Yeah, I love it. All right, so this is great. I can see people are already in the mindset of thinking in terms of graphs. So yeah, let's go ahead and move on. So as we're going to see, a lot of the operations that we do on graphs are going to be virtually the same as we've been doing on trees. Now, there's a couple of changes that we'll have to make to represent the fact that you might have cycles and that some of the structure can be more general than for trees. But the two tools that you will use throughout is depth first search and breadth first search. And I'll give some quick examples of that, but the pseudocode is going to be very similar to what we saw with trees. So we'll start with breadth first search. So same as for trees, the idea here is that you start at a node and your goal is going to be to traverse to all the other nodes connected to it in the graph. Now, breadth first means instead of basically from this node, we're going to first go to all of its neighbors, and then we're going to go to all of those neighbors' neighbors and kind of expand outwards. So in this example, we're starting with 2. And just as we did before with trees, we're going to have a queue, which is basically all the neighbors that we're getting to. So we're going to, well, as long as we still have things in the queue, and you can think of the queue as kind of what are the nodes that we're going to visit next. So we're going to start at 2. We're going to put it into the queue. We're going to mark it as visited. Now that's one thing we haven't had to do for trees, because with trees, there is no danger that we would branch out and eventually get back to our node. However, if we're not careful, because there's a loop here, there's a cycle, we might do 2 again, and then we might do it again, because we can go from 2 to 1 to 3 to 2 to 1 to 3 and get an infinite loop. So to help with that, we're going to mark it as visited. We're going to have some flag. We can represent this maybe as a map from nodes to a Boolean, whether we visit it or not. Maybe we can actually store it as a flag on the node itself. Just the key thing is we want to have some way to track, have we seen it before? We've already seen it before, then we know we've processed it and we don't need to go to it again. So we're going to add 2 to our queue. We're going to mark it as visited. Now, iteratively, as long as there are things in the queue, we're going to pull the first thing off the queue. And then for each of its neighbors, as long as we haven't visited them yet, we're going to add them to the back of the queue and then mark them as visited. So what we'll do here, we'll start at 2. We'll go to 1 and we'll so we're going to add all of 2's neighbors to the queue. So we're going to add 1 to the queue, and then we're going to add 3 to the queue. Now, pulling from the front of the queue, we're going to start at 1, and we're going to add 4 to the queue. We're not going to add 3 to the queue because 3 has already been visited. We've already added it to our queue. And then from 3, we'd want to add 4, 1, and 2, but those have already been visited, and so we're done. So in this case, the order will be 2, and then 1, and then 3, and then 4. So we start at 2, we go to its neighbors, and then we go to the ones 2 degrees out, in this case, node 4. All right, and then depth first search. So this is very similar to trees. And again, we're just going to add our visited flag. Well, we can do this recursively. And as you can see, we get it almost for free using recursion. So in this case, we start at 2. Very similar ways we do with trees. We're going to mark 2 as visited. And then we're going to recursively depth first search through each of its neighbors that we have not visited yet. In this case, depth first search, we'll do something like 2, and then we'll go to its child 1, and then 4, and then 3. In this case, we actually kind of did all of them before we ever came back from our first recursion call. Great. Any questions about this before we start going into some interview examples? Cool. So as I mentioned, we're going to do one that is this example that I love, which is flights and cities. So suppose you have a directed graph, as we talked about, as people very, very astutely pointed out, representing cities and flights that connect them. So an edge starting in city A and ending in city B represents that it's possible to book a flight flying from A to B. So your goal here is, given a starting city S and a destination city D, return the least number of flights it will take to fly from S to D. So, does anyone have any ideas of how we might take this on? So I think often, yes, we taught you the ideas. Now we get to apply them in practice. So I think often, if we're stuck, just with any interview, it can be good to work through an example. So we have this thing right here. So let's look at one of the harder cases, which is going from 0 to 6. So we can see, kind of just by looking at it, from 0 to 1, from 0, we're going to have to go to 1. So that's fine. Now from 1, we could go to 3, we could go to 2. It's a little bit hard to know which one is faster, but if you kind of trace through it, you'll see 0 to 1 to 3 to 5 to 6 is going to be the shortest path. That will be 1, 2, 3, 4 flights. Whereas we could also do 0 to 1 to 2 to 4 to 5 to 6. And I think that's going to be 5 flights. So what kind of things that we've talked about might help us for kind of starting at a node and searching out to see what the shortest path to get to another node might be?
So an idea that I have is that you can sort of like keep track of all the path that you have been to, and as soon as you get to the destination, then you return the shortest one, because that's how you got there first.
Yeah,
I don't know what kind of data structure you can use though for this.
Yeah, so I think that's some good intuition. The idea being that you store kind of your distance you traveled so far, the number of flights, and then once you get to the destination, then you can try to return how many you've done. But what about just in terms of how we're traversing the graph? What technique might we use for starting at the source and trying to search outwards to find the destination?
I was thinking depth first search.
Okay, depth first search, that will work, but let's talk about how that will happen. So we start at 0, and then if we depth first search, we'll go from 0 to 1, and then from 1 we'll go to 2 because we're going kind of deep first. We'll come back. 2 we'll go to 4. 4 we can go to 1 or to 5, and then first of all, if we go to 1, then we'll have a cycle, but presumably we'll mark it as visited, so we'll skip that. 4 to 5 to 6. So I think if we do depth first search, the first path we'll find goes 0 to 1 to 2 to 4 to 5 to 6. So then what do we do? How do we return that right away, or do we need to keep searching?
No, we need to keep searching.
Yeah, exactly, because we found one path, but that's not necessarily going to be the shortest path. Now, one challenge with depth first search is that it'll be a little bit tough to mark what we visited. And so by that, I mean, if we go 0 to 1 to 2 to 4 to 5, we'll say that we've seen 5. But then we need to also find this path 0, 1, 3, 5, 6. So depth first search can work. There are ways to adapt it. You can kind of track the best path you're doing and try to find all the paths to it and then take the shortest. But what happens if we use a breadth first search? So what are all the nodes that we'd find in each, I'll call it generation of the breadth first search? So remember, as we breadth first search, we're going to start at 0. And then we're going to expand and add all the neighbors to the queue. In that case, that's just 1. Then we're going to expand it out again and add all of that generation's neighbors to the queue. So then our next generation will be 2 and 3. And then we're going to expand it out. It'll be all of their neighbors, which in this case is 4 and 5. So with each generation, what can we say about all the nodes in that generation?
that they have the same height or probably depth?
Depth, height, I think terminology, aside, I think what you're saying is exactly right. It'll be the number of flights it takes to get there. So initially, 0 takes 0 flights to get there. The next generation is 1. Those are everything 1 flight away. Then we'll go to 2 and 3. That's everything 2 flights away. Then we'll go to 4 and 5. That's everything 3 flights away. So kind of in every step, you can think of it as like we're expanding our bubble. We get everything 0 flights away, and then 1 flights away, and then 2 flights away. Because at every step in the breadth-first search, when we add the next generation, we're effectively just taking everything that we reached in 3 flights and saying, where can we go with 1 flight away from those cities? And that will be everything we can reach in 4 flights. So yeah, does this make sense? I know this is a lot because this is like really cool about the power of breadth-first search. You're kind of expanding your ring. You have your ring of everything 0 away, then 1 away, then 2 away, then 3 away. And because we're trying to find the fastest path, this will guarantee that we'll basically get to the fastest path, the smallest number of flights. And the first time we find the node, the first time any node enters our generations, we'll know that that was the shortest number of flights to get there. Unfortunately, I can't see everyone here, but any questions about that? I know it's a lot, and just kind of working through this is kind of the example I showed with going from 0, searching to 1, searching to 2 and 3, and then 4 and 5, and then the last generation 6. Make sense?
Yes, it does.
Yeah. So what's the implementation going to look like? That's very nicely segueing into this. So this is our code for the breadth-first search. This is not going to quite work for us, but this is just the general breadth-first search. So we start at a source node, and then we want to get, search through everything. So now that this is actually really close to what we're going to do, what do we need to adapt? So we're going to need to add in a destination. So we're instead of just having a graph and a source node, we're going to add in a destination. And now in addition, in our queue, instead of just storing the node that we plan to visit, we're going to also store how many flights did it take us to get there. So what does that look like? So we have our queue, we mark everything as unvisited, and then we're going to enqueue a tuple of the source node and 0. So this means, this is pseudocode. So we're going to enqueue a tuple that contains source node and 0. And that means it took 0 flights to get to source node. Then as we're going through our BFS, we're going to do it in the exact same way, but for each node that we're processing, we're going to now know not just the node, but how many flights did it take us to get there. Then when we add all of its neighbors, we add flights to V plus 1, because it will take 1 more flight to get there. So we kind of trace through here. We're going to start by adding 0, node 0, and it took 0 flights to get there. Then we're going to add all of its neighbors to the queue. In this case, its only neighbor is 1. So we're going to add 1 to the queue, mark 1 as visited, and say that it took 1 flight to get to 1. Then we're going to try to add all of 1's neighbors to the queue, which in this case is 2 and 3. So we're going to add 2 to the queue, and it took 1 plus 1, 2 flights to get to 2, and it took 2 flights to get to 3. Now we're going to pull from the queue, we're going to process 2 and say 4. It took 3 flights to get to 4. Then we're going to process 3 and say it took 3 flights to get to 5. Then we're going to process 4. 4 actually, both 1 and 5 we've already visited. So we're going to not do anything from 4. And then from 5, now when we dequeue 5, we know that it took 3 flights to get to 5. We're going to find 6. It took 4 flights to get there. This code actually needs one more if condition, which is here, if v equals destination, return flights to v. Because we're done. We found it. We've reached our destination. Cool. Any questions about this? Yeah, I think that's a reasonable way to think about it, Mark. I don't know if you want to unmute and describe that.
Oh, sure. Yeah, I was just playing a video game earlier, so this kind of came to mind. Like, you know, in some games, like, you know, you're in a certain area and maybe you have like a mini map and you can only see a little bit around you, and then everything beyond that is kind of like grayed out. You haven't discovered it yet. So like when you're in a certain location or at a node, you can see kind of a little bit around you, like your neighbors. And then you can go to something you see on the horizon, which is kind of analogous to moving to a neighbor. And then from that location, you see a whole bunch of new stuff, which is like the neighbors. And you know, as you kind of move through the world, you can, you know, there's different ways that you can do it, right? You can just hop, keep going forward, and that maybe be like DFS. And then like once you get to the end of the world, you come back and you know, try a different branch. Or you could do like BFS, where you say, I'm in this location, I see 3 things around me, I'm gonna hit the one on the left, then come back, and then hit the one in the middle, come back, then hit the one on the right and come back. And you know, then I will have expanded my horizon a little bit. I'll be able to see, like I'll have a whole list of new things to see, and then I can maybe keep going from there. I don't know if that was helpful, but that's kind of how I think about it.
Cool. So then a real quick analysis of this. So as we mentioned earlier, and I probably won't go into a full explanation of why this is the case, but the runtime will be O of v plus e, where v is the number of nodes and e is the number of edges. Now, the reason both BFS and DFS generally have this nice linear runtime is you're kind of, as you're doing a traversal, either BFS or DFS, you're basically going to visit each node and each edge exactly once. I'm not giving a full, 100% mathematically rigorous, but you're basically traversing through the tree or traversing through the graph, touching everything once. You never do O of n work on any individual node or any individual edge. So the runtime will just be linear in both the number of nodes and the number of edges. So now question, and we kind of talked about this a bit earlier, why didn't we do DFS? And DFS definitely would have worked. There definitely are ways you could do this, and it would basically take the form, when you do a DFS, you would find every single path from the source to the destination, and then you would store them all and then return whichever one was the fastest. The kind of the main thing is that it gets tricky because you have to deal with these cycles. It also, tracking which ones are visited is a little bit tough, but it would be actually a kind of interesting exercise if you're really interested to try to rewrite this as a DFS. I will say it will be a slightly more complicated code solution than this, but it definitely is doable. And then extension. So what happens if the edges have weights and we want to minimize the distance traveled? So right here, we treated every flight as equal. But what if every flight actually has a number of miles, or more realistically, a cost, and we want to minimize the cost that we have to spend on plane tickets to get from the source to the destination? Well, I'm going to go ahead and say this is way out of scope for this. That gets really complicated really fast. There's an algorithm called Dijkstra's algorithm, which I nearly guarantee you'll never have to implement during an interview. It's really cool. If you're like super excited about this, I would encourage you to read about it. But it actually does something pretty similar to what we described. Just the main thing is you kind of start at your source and you expand outwards every time, starting with the node that was closest to the one you had before, and then adding all of its neighbors to your queue. The only difference is now you can't just do a straight up breadth first search. You need to use something called a priority queue, which will, some of the things you add might actually be closer than some of the things already in your queue, and you need to visit those first. I'm talking at a really high level. It's really cool, but it also does get complex. Cool. So then I have some additional resources here. I think these are some great graph practice problems. I have the first one, find center of a star graph. Really decently straightforward, but it could be a great exercise to just kind of understand the structure of a graph, how they might give it to you in your preferred language. I think it's always good to do easy whenever you're starting on a topic. Easy when you're learning a new topic on LeetCode is not actually all that easy because you have new concepts, you have new ways of structuring data. Then I have a couple other ones. Number of provinces is also known as like the number of connected components. This is a pretty common question that some companies do ask in interviews. Course schedule as well. It's basically you have a bunch of courses. Each course might have some prerequisites. Can you, given this setup, explain all the courses that you need to take in order? And it's a really common problem to be asked in interviews. It's actually used in practice to resolve dependencies. For example, if one package needs another package to load, that package might need another package. How do you resolve those in a way that you can actually load everything? And then last one, and this one's actually a little bit tricky. I was tempted to call it medium to hard, but it's fun if you're really crushing everything and you want some that really makes you think about the structure of graphs. That could be a fun one. Cool. Any questions? And I think at this point, we're happy to take any questions about trees, any questions about graphs, any questions about general career advice or experiences or anything. And then if we do have time at the end, I actually have one more LeetCode problem that I could consider kind of live coding for everyone, but I want to make sure we have time for questions first.
Yeah, first of all, big thanks to the three of the lecturers here for presenting the lesson today. It was super wonderful and really makes this hard topic easy to understand with your explanation. So thank you guys so much for that. Okay, well, it looks like we got a question up from Malangu, so I'm going to go ahead and ask away.
All right. Thank you so much for today's session. I really enjoyed learning about graphs and trees. And I've got a couple of questions, and these are just outside of what we're learning today, but they're just more focused on just the day-to-day life of a software engineer. So I have three questions. So the first one is what are the most common data structures that you get to use on the job? And secondly is what are some of the resources that you go to on the job when you encounter a new programming language or framework or platform that you need to use? And then the third one, and this one's for Mark, is since you work in a health tech company, is there any knowledge that you have that you had to learn outside of just how it would be for a software engineer working in a tech, purely tech or finance company?
Sorry, I'm having unmute issues today. Yeah, I can start with that and maybe go in reverse. So yeah, I am at a health tech company. Specifically, we work on we're trying to make clinical trials faster and cheaper because apparently they're very slow and not cheap, which means that a lot of trials that could get run for drugs that could be on the market don't, because it's just too cost prohibitive for the pharma companies to actually run the trials. So so yeah, I came into this job with no knowledge of the healthcare industry at all. And I've definitely had to learn a fair amount of that, just like knowing the different players in the industry, kind of how trials get run. You know, to be honest, a lot of it doesn't really affect my day-to-day. Like at the end of the day, I am mostly just writing software. And, you know, I have like a product manager who knows much more about this stuff than I do. So like, you know, I can always ask her like questions about the industry if they're relevant. But yeah, like I think the main thing where kind of industry knowledge comes into play is just when thinking about maybe requirements. So for instance, I'm right now working on a project to archive some of the data in our database. And so I had to think about regulations in terms of data retention, because there are regulations around like how long we need to keep this data in some type of accessible form. But like kind of once that part's figured out, when it comes to actually writing the software, I think that's much more in line with probably a less heavily regulated field. Was that helpful? Or did you have any follow-up there? I'll take the.
Mark, I think you muted. Go ahead. Oh, you're good. He said it.
Oh, okay, cool.
Yep.
In terms of data structures, I might grab that one.
Sure.
You know, I think by far arrays and lists are like very common. I think it's very unusual that, you know, it's not at all uncommon in a day to do some sort of array operation or list operation, concatenating them together. Probably the next most common are strings, you know, just random operations on that. Often pretty simple, not super algorithmically complex, but, you know, getting very comfortable with that. And then I think beyond that, it's really just having your tool bag, your arsenal of things. You know, I think the number of times I've used a binary search tree is like 1. But it was really nice to have it when I wanted to use it. And that was, you know, it's great to be able to pull that out and use it. Now, was I able to write a like self-balancing binary search tree from scratch myself? No. Did I need to? No. There were great libraries for me to use it for. But it was really crucial that I was able to understand, oh, this is a great tool that actually makes this problem really easy. And I can just like, you know, import BST or find some open source library in GitHub, pull it in, it works out of the box. That's awesome. Yeah, sets I do use. Dictionaries, hash maps, actually, I should say, are very common as well. And then do I use regular expressions? Yes, it all depends on the problem. Definitely great thing to pull out whenever I need it. I will say, I think I've never written a regular expression without having to look up all of the like special characters and how to use it every time. And there's some great online websites that let you like test a regular expression that I basically have to use every single time I want to write one. But yes, it's great to have those when I want it.
Same. I've also used that website as well for like regex expressions. And yeah, I'd like to add like hash maps and like JSON structures a lot too, like traversing JSON, which is essentially just a hash map with a bunch of arrays of hashes as well within. So I handle those quite a bit. So I saw 2 questions actually. One was a while ago. Someone asked about if you can do a solution like recursively versus iteratively, which one to do. I feel like from what I've seen, I've never really used recursion in a professional setting. And the reason for that is iterative approaches are often easier to understand, especially when like someone new is coming in to look at your code. That's one reason to use iterative. It's also just a little easier to understand and maybe a little easier to debug and come back and add to. So, but again, for interview sake, it's maybe personal preference. And then I think I saw a question about like work culture. and stuff like that. And someone specifically asked about Block, which is where I work, something along those lines. But oh, favorite and least favorite things about working at Block. So this kind of ties in. My probably favorite thing about working at Block, or one of them, is the culture. The culture on my team specifically is like pretty laid back. Our work-life balance is great. We have unlimited PTO, so if anything ever comes up, or you know, we have a vacation or something, there's no need to worry about PTO, which is great. And also, like, if I have like a doctor's appointment or if a family emergency comes up, they really stress like taking care of yourself first, especially amidst a pandemic, before, you know, taking care of your work. And you know, the reason for that is that if I'm able to take care of myself and be happy in general, I'm going to be able to put in kind of better hours as I'm working, kind of focus better, stuff like that. So that is definitely something that I see at Block. Also, people are pretty friendly too. I'm able to ask questions on other teams a lot, and people are very happy to help. And yeah, overall, just a good culture. And I'm also learning a lot, so that's great. Least favorite thing, I've only been at Block for like 6 months, so I don't know if I have like a least favorite thing. I think maybe least favorite thing. So Block has, we have Square and Cash App, but we also have like Tidal and Afterpay and like one other thing, I think. And I really don't work with those other companies as much. I specifically work for Square. So I guess maybe least favorite thing, it's probably my fault, but like I don't really know a whole lot about those other branches of Block. I'm sure there are resources for me to go out and find that, but I just don't know. It's a big company, so what can you do?
All right. Yeah, good, great questions and you know, answers so far. If I could also facilitate one more question, which is, you know, for those of you know, like, how did you prepare for like your interviews when you like first entering the industry, or you know, now that you've been in the industry for a few years, like, what advices would you give to incoming engineers to succeed in their jobs?
I did do a lot of lead code. Unfortunately, that is a very good way to prepare for your interviews. It's not always the funnest, but we are fortunate to be in an industry where we can prepare for these interviews and we can kind of know more or less exactly what's going to be on these interviews. So I did do a lot of lead coding. I did have to go back and kind of take a course on some of the fundamentals that I had forgotten since being in school. So that also helped me a lot. But because of that, having those fundamentals back under my belt and also practicing that lead coding, it does make my actual job a little bit easier because I'm just, you know, a slightly better programmer than I was before I started doing interview prep.
I think really, unfortunately, there's no substitute for a ton of practice and doing a ton of leak code problems. Whenever you can, do mock interviews. You know, when I was in college, my roommates and I, who I had the great fortune that they were all in tech as well, we basically did like mock interviews with each other where we'd pick a random leak code problem and like run it like a mock 45-minute, sit down, make them code it or whiteboard it. And that also makes it less stressful when you're actually in the interview. If you've done 10 mock interviews, the interview starts to feel a little more like those. But yeah, totally. Chance for a software engineer to mess up the company's code base. I love this. There always is, but if that does happen, it is not the software engineer's fault. It is the company's fault overall. By that, I mean, yes, there should, in theory, there should be a review process. There should be a testing process. You know, if, for example, a new hire or an intern or something manages to take everything down, something very severely went wrong with the review process, with the deployment process, with something else, it is really not on the intern or software engineer. And I think most good repeatable tech companies should have that culture in place where they know, interns are going to make mistakes. That's part of being an intern. New hires are going to make mistakes. That's part of being a new hire. That's part of the ramp up process. There should be guardrails in place to make sure that doesn't happen.
Hell, senior software engineers make mistakes.
Yeah.
Like people get tired. They, you run the wrong script, do whatever. Like, yeah. But there should be, guardrails and processes in place to prevent that from happening. There should be backups. Yeah, like if something goes catastrophically wrong, it's never one person's fault. It's a process problem. And any good company will recognize that and try to improve the process rather than punish the person who found the hole in the process. I don't think I answered the question about interviews. I think my advice for interviews is probably just be honest and upfront as much as possible. Like chances are you're not going to know everything. And if you try to bluff, it's very obvious. And it's okay to not know everything. I think the most important part, at least being on the other side of the table, like I want to work with people who are trying to learn. So like, and trying to improve themselves. So it's totally okay to say, this looks like something I've seen before, maybe from the stuff like, it seems like I could use a tree. I don't totally remember how to implement a tree. And your interviewer might say, okay, like, feel free to Google it, or here, I can give you some tips. And like, that's a much more productive interview than just trying to bluff your way through, because it doesn't work. Yeah, I think that's what I got.
Yep, awesome. Yeah, thank you for sharing all these insight about like how to prepare and how to also kind of face interviews and just as Mark said, like be upfront about it, because that's how you make sure you don't put yourself in a hole. So yeah, and also really like the conversations about just kind of confronting the fear about breaking something at work. As Marcus said, it won't be a hole. Like if anything, it's like one of the hallmark sign that whether like a company treats someone's mistake as a collective responsibility versus the individual responsibility. A good organization would make sure that it's a collective responsibility. Like if you made a mistake, there should have been some kind of review process or infrastructures and system that should have prevented you. And if it still did happen, then they should also do some kind of retrospective or postmortem to make sure, like, how do we like learn from this mistake and how do we make sure that doesn't happen again? So that's how you're working at a good organization that make you feel safe to work there and like learn from working there. So yeah, just wanted to put it out there because I also get like us like a junior engineer like breaking something in in production is like is one of the worst nightmares, right? And like makes you feel really stressed and even like fearful about keeping your job. But
it's also a rite of passage, though.
Right, it's also
It's
a rite
gonna
of
happen.
passage. Like it's a matter of time before you make some kind of mistake that breaks some parts of production. So. All right. Yeah. Any other questions that that any of you wants to raise for the lecturers?
I can answer the question that was just in the chat really quickly. For Block, at least, that has different companies, and they're wondering if there are different offices, I think, for the separate companies. Yes, for us, we do have different office locations for different branches. I think that we have access to all of the offices, like my badge can get me in, but for the most part, they're pretty separate.
Yep. And I think this also kind of like applies to like a lot of like other big tech companies. Also, one of the silver linings of like pandemic has been that like a lot of organizations also went fully remote or remote first, in that you can just work from any like location of your choice and the company would be totally fine with that. I know there's like, shift starting to move back into the office like these days, but still like it just opened up a lot of companies to that new possibility of working. So yeah, it's more opportunities like, even if you like want to stay in your hometown, but want to work for like company that's headquartered in like big city, that's totally a possibility now. So yeah, just another good thing about working in tech, I guess. All right. Any other questions? Is Marcus doing the light lead code problem?
Yeah, I can. I can do it. I'm okay going a few minutes over if as long as the Zoom room is not going to kick us out.
Okay, well, how about this? We're gonna just wrap up the official session for now. So, if like anyone you have to leave, that's totally fine. But if anyone wants to also stay around and just watch Marcus do like lead coding, that would be fun as well. So, but let me just wrap up the official session now. Thanks once again, everyone for joining, and thanks to the 3 of the lecturers who joined today. Yeah, really appreciate you guys kind of sharing this knowledge. I guess like just 2 announcements in terms of logistics. One, we'll actually have a break next week, so due to spring break. So the next lesson will be on April 24th. And then after that, we'll have like our final kind of like lesson on May 1st. We'll have like guest speakers and whatnot, and just wrap up a cohort. So you're just putting out the schedules out there for everyone. And then one more thing, if you haven't filled out the survey for the classroom, please do so, because we will really appreciate your feedback and kind of like incorporate into how we want to kind of structure the future lessons. So thank you guys. Thank you if you could really get on that. But otherwise, thank you guys so much, and feel free to stick around if you want to kind of watch the live coding session. Okay.
And I think this may actually be a little bit on the quicker side.
And Mark and Hannah, you guys don't have to stay on if you don't want to.
I want to see how this goes.
Okay. Yeah, so this might actually be a terrible idea, coding in front of everyone, but you can all, it's a nice encouraging environment. All right, can people see my screen here?
Yep.
Okay. And I want this to be interactive. I said I'd be coding, but I want other people to, I'm gonna ask for ideas, and we'll see if we can come up with a solution together. So yeah, so this is a nice classic tree problem where the setup is fairly simple. Given the root of a binary tree, return its maximum depth. And the definition of that is the maximum depth is the number of nodes along the longest path from a root node down to a leaf node. So we have this example here. In this tree, the maximum depth, I believe, should be 3, because you can go from 3 to 20 to 7, and you have a path of 3. I guess you could also go from 3 to 20 to 15 and have a path of 3 there. All right, so if we were just given this in an interview, what ideas might people have in terms of how we can start?
Well, like a lot of depth relates to the height of a tree, right?
Mhm.
So let's say, and since like recursion like is like a much easier thought, like you like could find the height of like the left and the right subtrees, and then like if like the left subtree isn't there, then you know that the height of the right subtree, and I think you have to do +1 as well for the root, right?
Yeah, so I think I was hearing a lot of great ideas there. So I heard recursion, I think, and this is intended to be a great example of a time where recursion will make problems like these significantly easier. You talked about a left tree and a right tree, and then +1. So yeah. Do you want to continue off that, or anyone else, and kind of lay out a pseudocode algorithm?
Yeah, I mean, I can keep going, but if anybody wants to, like, feel free to.
I think you're on a roll, Sanjana.
Okay, yeah. So like I'm basically like the first thing that I thought of was like right. So like basically like there's really like 3 ways to like go about. I mean, there's like 3 like separate like if statements that I'm thinking of. Like first one is like check check if like the left subtree exists. Yeah, and like if it doesn't exist, then like return the depth of the right subtree plus 1. Check if the right subtree doesn't exist and return left plus 1. And if both exist, pick the max and then just plus 1 to that. I think like one of the best like ways to start off is check if root is null, right? Because if root is null, that means we have to return 0. So it's like I like mention that because like that's kind of like the base case, quote unquote.
Yeah, I love this. I think I'm seeing the solution you described sounds great. And I'm also seeing a great idea in the chat about use a BFS and increment a counter and return the max. That would also work perfectly. So the idea there, and this is to be clear, a different proposed solution, you start at 3, you're going to kind of do your BFS, and the next generation will be 9 and 20. The next generation from there will be 15 and 7. And so you kind of keep searching out, and then basically the furthest one you get to is going to be your depth. So that would definitely work. I am going to jump the gun and say that will actually be a little bit longer to implement. But I think if that was your idea during an interview, that would definitely be a great solution, and you should definitely code that, and that would be a great solution to this. But I'm going to go with this recursive solution because I love showing more examples of recursion. And yeah, and so I think we have another max of depth of left and right subtree, which is also correct. But as Sanjana said, you need to add 1 to that. So the key intuition here with our recursive step is if you have an arbitrary node in the tree, just consider the subtree starting at that node. And the way you'd want to find the maximum depth of that is you take the max depth of the left subtree and the right subtree, whichever one is greater, that's the path in which your max depth is going to go down. And so it'll basically be the depth of that subtree, but then plus 1 because you're above it. So in other words, in this case here, the depth of the tree starting at 9, that subtree is just the single node 9. So that's going to have a depth of 1. The right subtree, the one starting at 20, that's the one containing 20, 15, and 7. The max depth of that is just 2. And so from 3, we see we have a left subtree with a depth of 1, a right subtree with a depth of 2. So the right subtree is deeper, and our depth is just going to be that plus 1. So 2 plus 1 is 3. So let's see if we can code this. So our recursive call is going to be something like return the max depth of this, max depth of root.left depth of root.right. And then we need to add 1 to it. And I actually don't code in Python at all. I'm not sure if we need self. So this is the general idea. Now we're not done. And Sanjana already mentioned this, but what are we missing from our recursion?
The base case, or base cases.
Base case, exactly. If we do this, we will either hit errors or get into an infinite loop. So what does our base case need to be?
I think that goes back to what I said earlier. Like you like actually want to check if the tree exists, right? So it's like there a node or not. Sorry, like root or not. Yeah, that's what I meant.
So if we don't have a root, this is basically base case. Return 0, exactly. There's nothing here. Okay, so what do we have here?
I like don't know if like this is also a good idea, but it's like I think the way that I was thinking is what if you don't have a right like subtree or a left subtree? Like how would this play out? Or like is like there not a need to address that since you're taking the max anyways?
Exactly. So this is definitely something you should think about. So as we're tracing through this, we should think, what if root.left doesn't exist, but root.right does? Well, in this case, when we recursively call max depth of root.left, that's going to be none. And so this will just be 0. And this will be something greater than 0. And so we'll be taking that. So this will actually work as we want it to, and we won't have an issue there. but you're spot on that you should trace through your code and think about exactly that case. You know, if we were structuring it slightly differently, then we might need to address that case special. But as it is,
Yeah, no,
this works.
I like thought so too, but like the like way that I was thinking about it was like taking it like part by part versus like just finding the max and then adding one. But yeah, no, that's a really good like way to really compress the. So yeah.
Okay, and I'm scared there's going to be some bug, but let's just try submitting it for fun. Oh, and there we go. We have a success. So this solution ended up being a very small number of lines of code, which is awesome. And this is really kind of the power of recursion. Because we're able to get the answer to the top problem by breaking it into subproblems, getting the answer to those subproblems, and then combining them together, this got really easy. And yeah, and we could have done this with BFS. We would have just had to bring a queue in. It would have worked great. And yeah, I don't think the BFS, for example, is a worse solution. But I love this because this just shows the power of recursion when you have something that so neatly decomposes into, you know, subproblems that we can just recursively call. And then I'm not going to spend a lot of time on this, but the runtime efficiency of this will be just O of n, where n is the number of nodes, because we're basically going to be tracing through, and we're going to traverse this and hit every node exactly once. Cool. Any last questions about this? Does everyone understand why this works? Awesome. Cool. Well, it's always fun working through LeetCode. I'm glad this one was straightforward enough that it was able to work. And yeah, and if you're excited about this, I highly recommend you check out the linked problems that we linked from the presentation. There should be a good mix of easy and mediums that you can use to you know, just test your and reinforce that understanding of trees and graphs. Great. Thanks, everyone. This will wrap up the informal session, but thanks for sticking around and have a great weekend, everyone.
All right. Thank you.